All right, welcome to our practice with section 2.2.1, which is a lesson on transformations of parent graphs like we already saw in class. So this is an extension of what we did in class and the extra practice. So in this video, I will be doing all of the problems for these graphs on the left side, and then your homework will be to complete this and do all of the problems on the right side. So in doing that, you guys are going to see me do an example of each different type. So you'll see me do an example with a cubic function. You'll see me do an example with this rational function, as well as the two types of functions on the back of this too. So you'll get to, hopefully between me doing it once and then you doing it, you'll feel pretty confident in your ability to graph these parent functions and the transformations. So let's start by just reading the directions so that we're clear on what I'm asking you to do on this worksheet. So on each graph, I want you to graph the parent function, and I want you to graph a new function with the given transformations, and then write the equation for the new graph. So I'm kind of asking you to do three things. The first one is graph the parent function. The second one is graph the function with the given transformations, and then the third thing I want you to do is write the equation for that transformed graph. So looking at number one, the parent function is y equals x cubed. So we're going to look at the parent function of this, and I want you guys to eventually be comfortable knowing what the sketch of x cubed, the parent function for a cubic, would look like. So the best way to go about graphing a function that you are not really familiar with would be taking some x values and getting those y values that result. So I'm going to make a table right here of x, y values and graph the parent function. So let's say I started with 0. I plug 0 into this function. That's an easy one to start with. I cube 0, meaning multiply by itself 3 times, 0 times 0 times 0. That's also 0, so my first coordinate is 0, 0. Let's plug 1 in. Cube 1, that's 1 times 1 times 1. The output of that is 1, so I have the ordered pair 1, 1. Let's plug 2 in. Now I'm cubing 2, meaning I plug 2 in for x, and 2 times 2 times 2. 2 times 2 is 4, times 2 again is 8. So 2 cubed is 8. So I plot that point. So if I continue on with 3 and then I cube 3, that's going to be a pretty high y value. That would actually be 3 cubed is 27. So instead of continuing with positive with x values, I'm actually going to plug in -1 now. Now when we plug in -1 cubed, I'll do some work up here. -1 times -1 times -1. Well, -1 times -1 is +1, because a negative times a negative is positive. And then I multiply it by negative again, -1, and I result with -1. So the ordered pair -1, -1 is on here. And likewise, when I plug in -2, -2 times -2 is +4. But when I multiply by -2 a third time, I'm back with a -8. So -2, -8 is the next point. So now we can see a pretty clear graph of this, what this is looking like. Let me get a pointer here. So this graph is going to start down here, and then it kind of squiggles through the origin and continues on. So I'm going to try to sketch a smooth curve of this. This is the parent function x cubed, also known as a cubic function. So that's my function, and now we want to transform that function by shifting it 2 units down and 1 unit left. So that just means I'm going to take every single point and then go 2 down, 1 left, and plot a new point. So I'll do that in red. I'd like you to switch colors as well if you have colored pencils or maybe a colored pen. That way it's just easier to see the difference between these two functions. So I'm going to shift down 2, left 1. So I'm translating the point -1, -1 first. And that will end up right here. Now I'm going to transform the point 0, 0 down 2, left 1, the point 1, 1, down 2, left 1. So now I have those 3 points. Come down here to the point -2, -8, and translate that one, down 2, left 1. And same with the point 2, 8, down 2, left 1. So now I've got this new function in the pinkish color, and if I sketch that, let me try that again. I can see the transformed function there. All right, so the last step is writing the equation for that graph. So we saw in class all the different types of transformations on several different parent graphs. And on cubics, let me delete a couple of things here. So we saw on the cubic functions from class that the parent function for that would be, with the transformations, a times x minus h cubed plus k. Very similar to that of the parabola, but it's just x cubed now. So it's still the same. The h and k values are basically what's happening to every single point. So we went down 2 and left 1. That means my k, the vertical shift down, would be -2. And the shift to the left of 1 would actually mean h is -1, which means I would plug in x minus -1, which ends up being x plus 1. So to clarify, the 2 units down right here means that k equals -2, the vertical shift is k. 1 unit left, that means h equals -1. So we're moving 1 in the negative direction, 2 in the negative direction down. So our equation would be y equals, and the value of a is just 1. So we didn't stretch this function at all. We just took it and shifted it down to left 1. So that would just be x minus -1, which ends up being x plus 1 cubed, and then -2 for that vertical shift down. So this should put you in a great position to do part B, and you have all of these points for the parent graph. So it should be very simple to sketch that parent graph now, and then you'll apply these transformations. The only difference here is I'm asking you to reflect over the x-axis, so make sure you look back at your worksheet from class if you're not sure how to do that, as well as a stretch of 2, which is going to affect that value of a. All right, moving on to the next function, parent function, which is y equals 1 over x. We actually did a graph of this early on the first or second week of school. Again, we're going to have 3 steps here. The first one is graph the parent function, then graph the transformed function, then write the equation for the transformed graph. So the parent function, y equals 1 over x. So you may need reminded of what this function looks like. You could also plug in some values of x and get the output values if we wanted to, and that's helpful when you're doing transformations as well. So first of all, let's think about plugging in the value 0. And what would happen here? Now we have x in the denominator, so I cannot plug in 0 because we can't divide by 0. That's an undefined value. What happens if I plug in -1? That would be 1 divided by -1, which is just -1. So -1, -1. What happens if I plug in -2? That would just be 1 divided by -2, or -1/2. That would put me right here. How about if I plug in +1? That would be 1 divided by 1, which is 1. Plug in +2, that would be 1 divided by 2, which is 1/2. I could plug in 3, and it would be 1 divided by 3, which is 1/3. And we'll see that this is going to get closer and closer and closer to the x-axis, also called the asymptote. And you hopefully are recalling that this function looks like this. And then in this quadrant down here, it looks like that. So I'd say when it comes to translating points, the easiest 3 points to translate are these. I think it's worth noting that both pieces of this graph are sort of centered at this origin, and I'm going to keep that origin in mind when I perform this transformation, 3 units right. So when I translate this entire function 3 units right, I'm going to keep in mind, where is this kind of central point of my function going to be? Here I have 2 asymptotes at one vertical asymptote here going up and down. The function never actually touches that. I'll do it in green instead. And this horizontal asymptote as well. Now those asymptotes are going to shift just like the function shifts. So this shift is 3 units right. So I'm just going to take this graph and just pick it up and move it over 3 units, everything on that. Then I'm going to reflect it over the x-axis. So my new points, so let's see, I've got this point. Actually, I'm going to translate my central point, kind of like this focal point at 0, 0, is now going to be shifted right 3 at 3, 0. Then I'm going to shift the point, I'm going to put that in blue, 1, 1. I would shift over here 1, 2, 3, but the next thing it says I need to reflect that over the x-axis. So instead of taking this point and going 1, 2, 3 and leaving it there, I'm going to reflect it, and it's going to land down here at 4, -1. And let's take this point right here, 2, 1/2, and I'll go 1, 2, 3 over, and then reflect that over, and it ends up right here at -1/2. And then let's think about how this graph is going to actually come together. So I've shifted this horizontal asymptote over 3. This green asymptote is now over here. So I'm going to draw in the asymptote. I have not shifted up or down, so my horizontal asymptote at y = 0 is still there. And now I have this asymptote here, and I can piece together what the rest of this graph is going to look like. And then the other half is opposite of that, so that's going to be up here. Just like these yellow pieces were opposite of each other, the red new pieces that have been translated will also be opposite of each other. All right, so now we just need to write the equation of this new graph. And again, let's look at what we're going to do here. So the first is 3 units right. That means my value of h, the value that I'm shifting horizontally, is +3. So I'm going to write that in here. H equals +3. And then reflecting over the x-axis, that means what I'm going to do is basically negate the entire function, which means put a negative out front. So that means instead of regular 1 over x, I'm going to have negative. That's the reflection over the x-axis. And then 1 over x minus h, and our value of h was 3. So this shift right of 3 is seen right here in the x minus 3, and the reflection over the x-axis is determined here by this negative out front. All right, moving on to the where here we're looking at the square root function as our parent graph. So the square root function, again, I'm going to start with a table to sketch my first step, which is my parent function. Then I'm going to use that graph to transform the function based on what it says, 5 units right, 2 units down. Lastly, I'll write the equation for the function. So we've got the parent function, y equals the square root of x. I'm just going to do a quick table here for values. And now taking the square root of a number, we can only take the square root of non-negative numbers, meaning positive values or 0. So I can plug 0 in here. And when I take the square root of 0, I get 0 out. And now I'm going to think of the next x value that I can plug in that is a perfect square, meaning I can take the square root of it and I still get an integer result. So, and that would just be the number 1. The square root of 1 is 1 itself. Then I want to think of another perfect square. The next one, moving up the x-axis, is not 2, not 3, but 4 is a perfect square. So I'm going to plug 4 in, and the square root of 4 is 2. And then let's get one more point in. So 5 is not a perfect square, 6 is not, 7 is not, 8 is not, but 9 is a perfect square, and the square root of 9 is 3. So over 9, up 3. All right, so we have this piece of the square root function. Notice I'm not putting an arrow down here. This is an end point. The function does not continue in that direction. That function stops right there at 0, 0. That's an end point. So I have my parent function graphed. This is the graph of y equals x squared, and now I'm going to transform it by shifting it 5 units right and 2 units down. 5 units to the right means that, let's see, let me write out my parent transformation function, a times the square root of x minus h plus k on the outside. Just a review of what we wrote down from class. Now this x minus h is determined by my horizontal shift, right or left. I'm going 5 units right, so h equals positive 5. H equals 5. So when I put that into my equation, there's no stretch or compression, so I don't need to change the value of a, which is 1. I will write x minus my h value of positive 5, so x minus 5. And then this shift 2 down means so down 2 means k equals negative 2. So that will be negative 2 on the outside of the square root. And I forgot to graph my new parent function, so everything's going 5 right and down 2. So this point 0, 0 is going to come from the origin, 5 right, down 2, right there at 5, negative 2. And this you can just kind of do visually, over 5, down 2 for every point. So 1, 1 goes over 5, down 2. 4, 2 goes over 1, 2, 3, 4, 5, down 2. And then this point, 9, 3, it's hard to shift that over 5 because my graph ends, so you could just use the 3 points we have right now and just extend it out a little bit with your arrow. So that's the transformation on number 3A. All right, let's do one more transformation with the absolute value function. So this function you may not have spent a ton of time with, but since we did review it in class, you should be a little more familiar with it right now. Remember, absolute value measures distance away from 0, and distance is never a negative value. You can't travel a negative distance somewhere, but you can travel in a negative direction somewhere, but not distance itself. So when we plug in some x and y values to the absolute value function, let's plug in 0 first. So how far away is 0 from 0? It's 0 units away, so I have the point 0, 0. How far away is 1 from 0? 1. How far away is 2 from 0? 2. How far away is 3 from 0? 3, and so on. So I see this absolute value, at least the right side of it, looking like that, but I can also measure the distance from how far negative values are from 0. So how far is negative 1 from 0? If I plug in negative 1, that's exactly 1 unit away. So a lot of people think of absolute value as making things positive. I plug in negative 2, absolute value makes it positive 2. I plug in negative 3, absolute value makes it positive 3, but that is not turning it into a positive. It's measuring the distance of these values from 0 on a number line. So that's why it's positive. So we end up with this funky looking V graph, and that is the parent function for absolute value. Let me make this a little more accurate. Okay, my points got a little off track. There we go. All right, so there's my absolute value function. Hopefully that the shape of that graph makes more sense to you after talking about that a little bit in class today. All right, so we want to transform this. We want to shift it 1 unit left. That's a horizontal shift, so I'm talking about the value of h. Let's write my parent function here. A times the absolute value of x minus h plus k. So 1 unit left in the negative direction, that means h equals negative 1. And reflection over the x-axis means I'm putting that negative out front. So it's basically going to take the whole thing and reflect it over this. So instead of being a V, it'll be an upside down V. But before I reflect it, I need to shift it left -1. So that means I'm going to take every point on here. So I'm going to take the point 0, 0, shift it left 1, and then reflect it over the x-axis, but this is on the x-axis, so it just stays where it is. Then I'm going to take the point, I'll work on this left-hand side first. So I'll take the point -1, -1. I'm going to shift it left 1 and landing here, and then reflect it over the x-axis, and I'm at -2, -1. Then I'm going to continue. Let's see my next point right here, -2, -2. I'm going to shift it left 1 and then reflect it. Now I'm 2 away on the positive side of the x-axis, so when I reflect it, I should be 2 away on the opposite side. So right here is where I'll plot my next point. And then you can probably see this pattern continuing. All these other points, as they get reflected, will move that down that way. Now let's go on the other side. So I'm going to start reflecting these positive values of x. So 1, 1, I'm going to shift it left 1, just like all the other points, and then reflect it, which gets me right here at 0, -1. I'm going to take the point 2, 2, shift it left 1, and then reflect. Now I'm 2 units above the x-axis, I reflect, and I'm 2 units below. And then again, you can kind of start to see visually all of this being pieced together. It's the same parent graph, it's just been shifted left. The whole thing has been shifted left. So this whole thing went over 1, and then everything got reflected, and now it's down here underneath the x-axis. So the equation for that, y equals, we didn't stretch or compress this, so it's just the absolute value of x. We shifted left 1, making our value of h -1. So x minus -1 is x plus 1. And then we did not shift it up or down, but we did reflect it over the x-axis, which means I should have a negative out front. So that's the equation for that one. All right, you have seen one type of every example on this page, and you should have what you need to now do the second problem of each type. So these 4 more problems, 2 on the front and 2 on the back in that right-hand column, I'd like you to do on your own, and I will check those out when I see you next time in class. All right, good luck.